the next speakers. So thinking now to carbon capture opportunities and particularly nature-based solutions, I'd like to introduce Professor Tony Bi, who's the director of the Clean Energy Research Centre. The CERC has been in operation at UBC for, I think it's about 3 decades now. It's one of our most established research centres. Professor Sue Baldwin, who's an expert in mine remediation. She's also involved in the mining microbiome program, looking at biomining and bioremediation of mines. And also Professor Gary Bull, who's a part of the Forestry faculty, but also an expert in carbon offsets and using forestry for carbon capture. So I'll hand it over to Tony as the first speaker, I believe.
No, I think it's Gary.
Gary.
Okay. My apologies, Gary.
Sure. So I'll share my screen now. Okay, and everybody.
Yep, that's great. Thanks, Gary.
See my screen. Thank you. Thank you for the opportunity to speak with you. I'm probably the only forester in the audience or somebody from the Faculty of Forestry, and you may be wondering why a forester would show up for a mining event. But the short news, and I can skip all the slides and tell you quickly that the real point of me being here is to show that there's an opportunity here for the forest sector to work with the mining sector in decarbonization. And the reason why that is the in forest, we have a lot of very low grade material that we struggle to manage and we don't know what to do with. And so there's a conversation that has started with taking that low grade material, transforming it into biocarbon, and then putting it out on mine sites that are close to where the forests are, which we are trying to manage. So that's really the big opportunity. Let me give you a little backup to that. I started looking at biochar back in around 2010 with a graduate student, and I was using a standard from the American Carbon Registry, which is a voluntary registry in the US. And so in case you don't know what biochar is, it's a charcoal that's produced from biomass, such as forestry and agricultural waste. It is a stable solid that enables long-term carbon storage, and it does benefit. The benefits it produces is water storage, improvement of soil health, assisting in releasing soil nutrients to plants. And since it's a method used for carbon offsetting, having a carbon accounting methodology can unlock carbon finance. So this is a 180-page methodology that then I took and applied to a forest in Ontario. And so on the right-hand side of the screen, you'll see a link through a MyTax project to that. And we wrote up a very detailed plan about how we could use that biochar methodology and create carbon offsets. So for those who are interested, I can provide more information on that. The other important theme for me in all of this, particularly in Canada, is how do Indigenous communities feel about this? And so I just want to highlight here this story of how Indigenous groups see this as an employment creation opportunity. And so this particular program for training Indigenous youth was led to about 300 man days of work, and it was very enthusiastically received by the First Nations community, and it became a logical way for them to participate in business. So back to my first project here. We then, there in Ontario now, there is something called Crye, which is the Center for Research and Innovation in the Bioeconomy. And so with that same project that I started back 2 slides ago, they have now gone to scaling it up to commercialization and producing high quality biocarbon for industrial purposes. This can be in industrial foams, it can be in coke, in the steelmaking process and so on. So there's a number of applications for biochar. And so this project value at the moment, and this is 2020 dollars, it was $3.3 million to take an old sawmill site and scale up the production of biochar. I want to highlight here in 2020, the United States Forest Service participated in a conference session with Ms. Dumrose presenting on biochar for mine site remediation. The key message outlined on the slides are that to restore many areas of disturbed forests, we need to produce biochar from essentially biological waste material. We need to link with a sector like mining, which can use the biochar for a number of benefits, and that biochar remediation done properly will provide revenue in the carbon markets and additional ecosystem services benefits. I would encourage you to take a look at the website that's highlighted at the top of the screen, which is the US Biochar Initiative Conference. And I will have the links in the slide deck. So in summary, I would say that the goal is to manufacture and use biochar materials locally. That's what makes the most economic sense. So the more we can co-locate forests and mining projects, it will start to make much more economic sense. As the speaker said, rocks can grow plants, even when you use, can grow plants when you use biochar. And finally, biochar can play an important role in remediating both contaminated and non-contaminated sites. So we really, there's a win-win here from a forest and a mining sector point of view. Another discussion I had last week was with Nextfour, which again is out of Ontario, which is advancing forest-based solutions. They are already engaged in biocarbon for heavy industry and would be very open to having a conversation with the mining sector and finding ways to collaborate in research. Here's an example from their webpage of the kind of some of the heavy industry partners that they're dealing with, as you see listed on the right-hand side. And it's all about trying to reach low carbon objectives. So I think there's a tremendous opportunity here for collaboration. So I will, at the moment, I'm involved in starting up a new carbon standard that will be a biochar standard by the end of 2021. This is being run out of Europe, and it will be a greenhouse gas accounting methodology for biochar run by separate groups out of Germany and the UK, and I will be advising them. So for those interested in that, I do know that the mining sector is a stakeholder in this standards development. And so with that, I will end and pass off my presentation to Dr. Tony Bi.
Can everyone see my shared screen now?
Yes.
Okay, great. Thank you very much. Chair, for the introduction, or for also give me this opportunity to share some of our work. So I will continue from Gary's talk. So he really talked about the application of the biochar for the decarbonization of these different industries. But for me, I'm going to talk about is how to produce the biochar or how to improve the performance of the biochar, okay, for these different applications. So the subject is very, very narrow from engineering point of view. I'm going to talk about the biochar from microwave-assisted catalytic pyrolysis of the biomass. So a very, very specific type of the technology we have been working on, okay? So let me tell you what is the microwave-assisted catalytic pyrolysis. So a lot of you probably are familiar how to make the charcoal, okay? It's an Asian technology, maybe 7 years ago, okay? Our ancestors already using the carbonization, okay, method, okay, using these very, very primitive kilns, okay, the kind of the soil kilns or mud kilns to make the charcoal, right? But it's very, very primitive. It took us about the days or weeks to convert the biomass, okay, to the charcoal, okay. Also at the same time, it emitted out a lot of the pollutant. So nowadays, people are still working on the we call it biochar or the charcoal production, but we try to develop modern, efficient, also clean technologies. One of the approaches we call the fast pyrolysis. So it will be taking about a second to minutes to convert the biomass to the biochar. At the same time, about more than 50% of this biomass feedstock will be converted to the bio oil. Then you can upgrade the bio oil to liquid biofuels. So from the decarbonization point of view, as Gary said, the biomass, the trees grow, will sequester the CO2 from atmosphere. So now when you burn the biofuels, it will release that. But at the same time, the biofuel will displace the fossil fuels. So that created the credit, or we call it avoid the burden. So that is part of the credit you can create from the biomass supply. At the same time, the biochar will be, for example, buried, okay, or stored in the soil for many, many years. So again, that will create a carbon sink. So overall, if you look into the whole process, you can create the carbon negative. Okay, so that is the whole interest nowadays about the biochar production and the biofuel production. Okay, then what is from the research point of view, what are the issues? So basically, we try to improve the quality of the biochar and the quality of the bio oil. Okay, from the engineering point of view, how do we improve the bio oil and the biochar quality? Okay, look into the bio oil. One of the way we try to do is introduce the catalysts. So you can modify the organic vapors produced from this cracking of the biomass to improve the quality, to make the upgrading easier, also to increase the yield of your biofuel products. How about the biochar? Okay, I said the charcoal is the Asian method, but how about the biochar? So how can we improve the biochar quality? So we have been thinking about a new method. We try to use the microwave heating to manipulate the process. Okay, everyone has the experience of making the popcorn. Okay, when you heat it up from inside out, then you create a chance to create a lot of the micro pores of the biochar product. Okay, we talk the internal heating. So that is the way we try to combine the catalyst with the microwave heating to improve the bio oil quality and the biochar quality at the same time. Also, by combining the catalyst with the microwave heating, we thought the catalyst can increase the microwave absorption and then for the biomass fitting. Remember, we talked about the carbonization takes days or hours, but fast pyrolysis are minutes and so on. So if we can increase the microwave absorption by the catalyst, we can also potentially increase biomass heating. Right? The biomass is very, very poor microwave absorption materials, but the catalyst can help that. Another one is how about catalyst? What kind of catalyst? Okay, you can imagine when you add the catalyst into the biomass, the catalyst may end up in your biochar. So can we select a proper catalyst? So once you make the biochar, some of the catalyst will remain in the biochar, which will not be harmful to the soil or to the environment. Instead, it may be beneficial if those catalysts contains the nutrient. So that will be beneficial for the soil application, either for the mining site repairing or for the agricultural soil application. Okay. So those are the hypotheses or the approaches we try to explore. Right? So with those ideas, we come up with this microwave-assisted catalytic pyrolysis of biomass. What you do is to properly select the catalyst. In this case, we use bentonite, is a natural kind of the particle or the material, or the potassium phosphate is a fertilizer. Okay, then we pre-mix with the biomass particles and then do the microwave pyrolysis. So we can produce the bio oil with the higher quality. At the same time, we produce the biochar. We call it indigenous biochar. I will show you the biochar will have a very high surface area that will be very, very good for the adsorption. Okay. Also high absorption affinity as well as rich in nutrient. Like I said, if we use the potassium phosphate and so on, or bentonite, which will add the value to the biochar. Okay. Then how biochar for the soil applications, we can improve the soil fertility, increase the soil water holding capacity, and increase the soil cation exchange kind of the capacity, as well as we can use this biochar to immobilize the heavy metals for contaminated soil. Okay, so I just share some of these results. We compare the biochar prepared from the conventional pyrolysis and the biochar prepared from the microwave-assisted catalytic pyrolysis. Okay, so first look into the bio oil. This is the viscosity of the bio oil produced from the conventional pyrolysis. This is the bio oil produced from the microwave-assisted pyrolysis. Because of the catalyst, we can see we reduce the viscosity. Means you reduce the content of the heavy hydrocarbons, make the upgrading of this bio oil easier. Okay, also easy handling. How about the pH value? The bio oil produced from the conventional fast pyrolysis has a very, very strong acidity. Okay, the pH is at 3.1. But if we do the microwave catalytic pyrolysis, the pH now is 5.6. Now very close to the neutral. Okay, again, it will make the handling of the bio oil much easier. This is because you reduce the acidic component in the oil. Say in the conventional pyrolysis, 25% is the acidic compound in the bio oil. But now with this microwave catalytic pyrolysis, it is reduced to 6% of the acidic compound content. Also interesting enough is we found we can substantially increase the phenolic compound from 11% from the conventional pyrolysis to 45%. The phenolic compound is a very, very good biochemical material, right, for making the plastics, okay, or the chemicals. Again, to increase this compound content, that will be increasing the value of the bio oil. How about the biochar? The surface area, I say, is directly related to the adsorption capacity of the biochar. It is more than 10 times, okay, of the increase in the surface area when you use the microwave-assisted pyrolysis. Then how about the nutrient content? I said the phosphate and the potassium are essential nutrient for the soil. Again, in the conventional pyrolysis, there is no such nutrient, but we can now add the value or nutrient value to the biochar if the biochar is specifically made for the soil applications. Okay, so also I add some other parameters or the properties here. So just quickly show you, say this is the biochar we made with the catalytic microwave pyrolysis. This is from the conventional heating method. This is the water holding capacity of the biochar if we blend 1% of the biochar in the soil. In this case, it's a sandy soil in British Columbia, in our province. This is a regular soil, the water holding capacity. This is blending in 1% of the biochar. You can increase the water holding capacity by 30%. Okay, this is a cation exchange capacity that basically represent the quality of the soil for the nutrient absorption or transmission of the nutrient to the crops. Again, you almost double, okay, this cation exchange capacity of the soil by blending 1 to 2% of the biochar we made from the catalytic microwave pyrolysis. This is extracted lead. Okay, once you blend in 1 to 2% biochar, the biochar will be strongly bound the heavy metal. In this case, it's a contaminated heavy metal. They make the extraction of the heavy metal very, very difficult. This is the regular soil contains heavy metals. This is after you blend in 10, 20%, 1 to 2% of the biochar. You can see the extractive heavy metal essentially reduced because the biochar now strongly bond those heavy metals in the soil. Okay, how about for the crop applications? Okay, so this is the crops. We cultivate the wheat in a kind of the controlled the chamber. Okay, these are the soil with the heavy metal but added biochar. This is just the soil. This is the soil with contaminated heavy metal. Okay, then we grow this wheat. Okay, seeds. So we measure the germination percentage, also the wheat shoot growth rate. Okay, so compare here. This is the regular soil. This is after you contaminate with the heavy metal. You can see the germination rate reduced. And here is the wheat growth rate. Also, once you blend in the heavy metal contaminated soil, the growth rate also reduced. Once you blend in 1 or 2% of the biochar, the germination rate recovered almost. Okay. Also, the growth rate also recovered compared to the heavy metal contaminated soil. Okay, this is contaminated soil blending in 1 to 2% biochar. This one is the lead in the dry kind of the biomass collected from this wheat. Okay, we collect the wheat, we dry it, and we measure what is lead content in the dry matter. This is the regular soil. This is regular soil with the heavy metal contaminate. You can see the heavy metal will transmit into the wheat, okay, the biomass. But once you blend in the biochar, you can reduce the transmission of this heavy metal into the crop products. Again, because of this heavy metal now, it's get fixed or get hold by the biochar blending in the soil. Okay, so this really just to give you a kind of overview what kind of biochar how the biochar can be produced, and how we can use the limited resource of the forest residues or the biomass to produce a high quality biochar, so that it can increase the efficiency of these biochar applications in immobilize the heavy metals, also improve the soil kind of the fertility in the future. Okay, so finally, I want to thank my student, Bad Mohammed, and my colleagues at the UBC Profs Tony Bi and Sang-Soo Kim, and also the funding from the Canadian Natural Science and Engineering Research Council and the Crye Institute of Science and Technology for supporting this work. We're currently building a pilot plant unit which has a capacity about 15 kilogram per hour of processing capacity. We want to further demonstrate and produce the enough amount of the biochar for some kind of the plot testing instead of just in kind of the laboratory tests. So that is the future development. Again, we will be happy to share our future result with all the attendees today. Thank you very much. Now back to you, John.
Yeah, thank you, Tony. We're just trying to keep to time, so we'll get Sue, and then after that, we'll see if we can get some time for some questions.
Okay, I'm just going to share screen. Can someone allow me to share my screen? Ah, okay. Okay, I'm assuming everyone can see my screen. If not, please shout at me to let me know. So yeah, thanks very much to that introduction from Gary and Xiao Tao. My name is Susan Baldwin. I'm a professor in the Department of Chemical and Biological Engineering at the University of British Columbia. And as John mentioned earlier, my research is in the area of mine remediation, mostly bioremediation. And in particular, I'm interested in nature-based solutions that are sometimes referred to as passive or semi-passive treatment processes for remediating mine sites. And today, the goal of my talk is to introduce you to some of the projects that we're doing using biochar for remediation. So yeah, we've heard a lot about biochar and that it can be made for pyrolysis or microwave-assisted pyrolysis from waste biomass. And that can include any type of biomass, not just biomass from the forestry industries, but biomass is produced from agri-food industries and in other places. And why is it so useful for mine remediation? I think you saw some information earlier about the specific surface area. So depending on the type of biochar that you have, and all biochars are different, they can have a very high specific surface area. And as an example, this could be thousands of square meters per gram, which is something when I tell that to my students, they don't think I'm making it up. And also the biochar has the presence of different, in addition to the carbon, it's got sort of different groups on the surface that can provide ligands for metal binding of nutrients, and all kinds of things. And also biochar is a scaffold. It's something that you can use, you can modify its own properties and by heating it up further and doing thermal and chemical treatments. But you can also use it as a scaffold on which to add things that give it new properties. And I'm going to describe some of those, give some examples of what I mean there. So the biochar, in addition to using the pyrolysis derived biochar, a lot of the biochars that we've been getting come from the pulp and paper industry. So it turns out a lot of the woody material that's not suitable for making the specialty papers that are made in British Columbia is used in some combustion units to provide some energy for the facility. And it turns out that there's incomplete combustion in these boilers, and which I guess on the one hand you could think of that as a bad thing. You're not getting enough, getting all the energy that you can out of the waste wood. But it also produces this product that almost looks like biochar. And this ash is collected in cyclones or electrostatic precipitators and can be recovered. Right now, they're not used for anything at all. And it's a waste material, it's a liability for the pulp and paper industry, and they are landfilled on the site. These landfills are becoming full, and this material is available for anyone who can think of a good use for it. And this also sort of feeds into another interest, which is the circular economy. How can we use wastes from one industry to benefit another? And how can we actually change our perspective of instead of considering these residues as wastes, but they are valuable and can be reused elsewhere? So the first example that I want to give to you today was an iron biochar composite that was developed that can remove selenium. So selenium is a constituent of concern at many mines, both metal mines and coal mines, and it needs to be tightly regulated. And this is due to its propensity to bioaccumulate up the food chain if it's released into the environment, and it can cause toxicity effects in higher order species like fish and birds. And so the actual concentration of the selenium that released into the environment needs to be very, very low, below 1 or 2 micrograms per milliliter. So in this example, the biochar itself, as is, and there's a bunch that we tested here. One was a regular biochar, and a few of these ashes don't absorb the selenium or remove the selenium from solution in any way. So the selenium, I should add, is present as selenate in the aqueous phase. This is the mobile form of selenium. This is the selenium that you want to get out of the water. And so what was done here was that we used the biochar as a scaffold on which to functionalize with iron, with Fe iron in the form of iron oxide. And so a procedure was developed using sort of chemical and thermal treatments to get the iron oxides on the surface. And this functionalized biochar, as you can see over here with these bars, was very successful at removing the selenium. So the regular biochar, which is just formed through pyrolysis, worked the best, but the ashes worked almost as good as the regular biochar. And so this provides an opportunity to remove this toxic compound from mine impacted waters at mine sites. And it also provides an opportunity to reuse all of this biochar that's produced at pulp and paper mills. This map over on the right-hand side shows that this is in British Columbia. Shows that there are opportunities to transfer the residues from the pulp mills to the mines because they're located quite close to one another. So the red blocks are the mines and the blue blocks are the pulp mills, and you can see there's a few places where they're very close to one another in the Kootenays and Kamloops area, even kind of further north. So the other example that I'm giving here, which took place at one of these sites here in the Kootenays, was that we're trying to develop new concepts for this passive water treatment that allows us to not only clean the water, but to recover the metals from the water. There's a lot of metals dissolved in these waters, and if you remove them from the aqueous phase, they still remain on the mine site, and they provide a liability and need to be managed. And so with these new treatment systems, you can kind of have a modular system and use the biochar. Here it was for zinc, so it was as an adsorbent, and we didn't need to functionalize the surface. And here we were binding the zinc directly to the biochar or the ash, with the idea that this could be incorporated into a modular system with also a biological step, because in mine water, I should add, there are other contaminants like sulfate and nitrate that might interfere with these processes, and that also need to be removed. So we can couple it with a biological process as well. And so this worked really well for getting the zinc out. And if the mine were to use this, they'd have the opportunity to remove the zinc completely off of the mine and then recycle and reuse it. And then the final example that I want to give here is how we might use a biochar to support bioremediation. So bioremediation is using microorganisms, naturally occurring microorganisms, that are able to take contaminants like sulfate, nitrate, or even metals, and turn them into non-toxic forms, pull them out of the water, rebuild soils so that plants can get nutrients and revegetate these mine sites. And in this concept, the biochar or the ash, again, is used as a scaffold onto which you can bind, or we can bind organic materials, or the nutrients that are derived from organic materials that are agri-food waste products. And so, yeah, the wood residues make the biochar itself. We bind onto the surface of it. Here's the C for the carbon, but it could also be nitrogen, phosphorus, and potassium. And then this enriched biochar ash can either be used directly in water treatment, or it can be added to mine tailings, for example, or disturbed mine sites to rebuild the beneficial microorganisms in the soil and reestablish vegetation. So those are just the few examples that I wanted to convey to you today, and I just wanted to acknowledge that this work was supported by pulp and paper industry in British Columbia, and also from a mining company. And also like to thank the postdocs and students and colleagues that helped with this work. Thanks very much.
Thank you, Sue, and thank you to Tony and Gary as well. I think in the industry, we think about what we do with our waste, but we don't often think about how we can use the waste from others.